Hi, welcome to the next video. So this lesson, we're going to continue 4.4, the fundamental theorem of calculus. So last video, we started 4.4, and so we started our work on understanding and learning the fundamental theorem of calculus. Okay? So I ended last lesson with giving you an example of a function g of x. This would be the integral from a to x of f of t dt. And so we calculated g of x for different values of x in an example. So here in this example, we're going to do a similar kind of thing. So if g of x is equal to the definite integral from a to x of f of t dt, where a equals 1 and f of t equals t squared, find a formula for g of x and calculate g prime of x. Okay, so g of x is that definite integral where a is 1, f of t equals t squared. Find a formula for g of x and calculate g prime of x. Okay, so solution. G of x is equal to the definite integral from a to x of f of t dt is given. Well, that's equal to the definite integral where a is 1, so lower limit is 1, upper limit is still x. F of t, which is t squared dt. So I just substituted for f of t, t squared, and substituted a for 1. Right, a equals 1, f of t equals t squared. So an antiderivative of t squared is t cubed divided by 3, and we're going to evaluate from 1 to x. So t cubed over 3 evaluated from 1 to x is equal to x cubed over 3 minus 1 cubed over 3. So that's x cubed over 3 minus 1/3. That's g of x. Okay? So that implies that g of x is equal to x cubed over 3 minus 1/3. G of x equals x cubed over 3 minus 1/3. Now g prime of x is just the derivative of g of x. So g prime of x is just the derivative of that, which is x squared. X squared. Derivative of x cubed over 3 minus 1/3 is x squared. So that's g prime of x. Okay? And so we found g of x, and we found g prime of x here and here, and so we're done. And sometimes mathematicians will generally draw a box to represent the end of a proof. Okay? Okay, so we've now done some work with this function g of x here. And so we're going to use that in the following theorem, the fundamental theorem of calculus. And so this is the main point, main topic of 4.4. Okay, so this is the fundamental theorem of calculus. And so the fundamental theorem of calculus is usually abbreviated FTC. It's an abbreviation from fundamental theorem of calculus. And this is part 1 of that theorem. Okay? So part 1 of the fundamental theorem of calculus. If f is continuous, on the finite closed interval a comma b, then the function g defined by g of x is equal to definite integral from a to x of f of t dt, a less than equal to x less than equal to b, is an antiderivative of f. That is g prime of x is equal to f of x for a less than x less than b. So that is part one of the fundamental theorem of calculus, abbreviated FTC. The fundamental theorem of calculus is abbreviated FTC. This is part one of that. If f is continuous on that interval, then the function g, defined by g of x equals the definite integral from a to x of f of t dt, from x between a and b inclusive, is an antiderivative of f. That is, the derivative of g, the derivative of this definite integral, g prime of x, is equal to f of x for a less than x less than b. That is the fundamental theorem of calculus. Okay, so what does that mean? Let's look at an example. Let's use it. Here's an example. Find the derivative of the function. Find the derivative of the function. G of x is equal to definite integral from 0 to x of the square root of 1 plus t squared dt. Okay? Find the derivative of that function. Solution. Since the square root of 1 plus t squared is continuous, g prime of x is equal to the square root of 1 plus x squared. Right? The condition for the fundamental theorem of calculus is that your function f is continuous. Then, if you take the derivative of the integral from a to x of that function f of t dt, then the derivative of g is f of x. And so here, g prime of x is just plugging in x here, square root of 1 plus x squared. Okay? The t here is called a dummy variable. So technically, this is a function of x. And so t is just a dummy variable because you're integrating from 0 to some variable x. X here is actually the variable. T is just called a dummy variable. It doesn't matter. I mean, you can call it anything you want. It's basically, this is dependent on x. Okay. So let's do another example. So this is one example of the fundamental theorem of calculus. And I'm going to put another example above it here. Excuse me. Another example. Okay, so the example. Markers weren't good. Find d dx of the definite integral from 1 to x to the 4th of secant t dt. So here, this problem has a bit of a trick in it. Okay. All right. So the solution. So the solution is that d dx of definite integral from 1 to x to the 4th of secant t dt is equal to plug in for this x to the 4th. So you get secant of x to the 4th times, now multiply by the derivative of the upper limit. This is a function of x and you're differentiating with respect to x. So multiply this by the derivative of x to the 4th. And what you get is secant of x to the 4th times 4x cubed. That's the answer. Okay, so the derivative of, with respect to x, of the definite integral from 1 to x to the 4th of secant t dt is equal to secant of x to the 4th times 4x cubed. Okay, there's a general formula. So we've now done two examples using the fundamental theorem of calculus part 1. As a general formula, let me put this formula here. And so you can use this formula in these situations. If you have a definite integral from a to a function g of x of f of t dt, and what you do is, this is f of g of x, so you plug in the function g in for your variable, so it's f of g of x times g prime of x. Okay, so the definite integral from a fixed number a, to g of x of f of t dt is equal to f of g of x times g prime of x. That's the formula. Okay, so for instance, in this example, so we're studying this, look at this formula, and above look at this example. The derivative, the formula is now, I need to add ddx. So it's ddx of that definite integral. The derivative with respect to x of the definite from a to g of x of f of t dt is equal to f of g of x times g prime of x. And so this is a formula. Okay. So you use that formula in these problems. So for instance, the derivative of this definite integral, here g of x is x to the fourth, and here f of t is secant of t. So here, f of t, so using my formula here, f of t is equal to secant t, and g of x is equal to x to the fourth, right? The a doesn't even matter. It doesn't matter what number you put there. So then, which is interesting, you can change this number and get the exact same answer. Okay, so then, this is about a rate of change. It has nothing to do with, okay. So f of g of x times g prime of x in this example, f of g of x times g prime of x, if you were to get this answer by just plugging into this formula, f of g of x would be secant of, and then for t, you would plug in for t g of x, and so you would get secant of x to the fourth times the derivative of g, which is 4x cubed. So you get that answer. Okay? So f of g of x times g prime of x gives you the answer of secant of x to the fourth times 4x cubed. So if you use this formula for these type of examples, you'll get the answer. Okay? Okay, I remember having difficulty with this problem first too. You just use this formula and you'll get the answer. Okay. Okay, so this is the fundamental theorem of calculus part 2. I'm going to abbreviate fundamental theorem of calculus here with FTC, like I mentioned before. This is the fundamental theorem of calculus part 2. So the second part says the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f. That is, capital F prime of x is equal to little f of x. Or just capital F prime is equal to little f. Okay. This is the evaluation theorem. So I'm just restating what earlier I had called the evaluation theorem. The evaluation theorem is part 2 of the fundamental theorem of calculus. So we're going to talk about that. Just giving it another name. So as far as an average value of a function, the average value of a continuous it doesn't have to be continuous actually, which is weird. So the average value of the function f on the interval a comma b is called f sub AVE f average, which is equal to 1 over b minus a times definite integral from a to b of f of x dx. Okay. That equation tells the average value of a function f on an interval a comma b. The f sub f is equal to 1 over b minus a times definite integral a to b of f of x dx. Okay, so that's the average value of f on an interval. Okay, so that's the second. Okay, so I'm erasing the second part of the fundamental theorem of calculus. which is also called the evaluation theorem. Let's do this example. Find the average value of a function. Find the average value of f of x equals 1 plus x squared on the interval, find and close interval -1, 2. So we use that equation right there. Okay, so f, which is the average value of that function on that interval, is 1 over b minus a, which is 2 minus -1, times the definite integral from -1 to 2 of 1 plus x squared, which is f of x dx. So I'm just plugging in 2 minus -1, different from -1 to 2 of f of x, which is 1 plus x squared dx, the right hand formula. And so this is equal to 1 over 2 minus -1, which is 1/3, times that definite integral. And so to evaluate this definite integral, you just take an antiderivative of 1 plus x squared, which is x plus x cubed over 3. And then you evaluate that antiderivative from the lower limit of the definite integral to the upper limit of the definite integral. So this is equal to 1/3 times x plus x cubed over 3 evaluated from -1 to 2. And so that's equal to 1/3 times this, when you plug in 2 for x, -1. For x. Okay, so you just plugging in 2 to that expression minus plugging -1 to that expression. And what you get is 1/3 times 2 plus 8/3, which is 14/3, minus, this is -1/3. -1 plus -1/3 is -4/3. So this is 14/3 minus -4/3. Okay. So 14/3 minus -4/3 is 14/3 plus 4/3, which is 18/3, which is 6. 1/3 times 6 is 2. So you get 2. The average value of f in that interval is 2. Okay, just from that formula here. Okay, so I'm going to call this diamond, this formula here. And so I use that formula right there for that equal sign. And then I just calculate that integral and multiply it by 1/3 and get 2. You get 2. Right, so this board is for finding the average value of a function on a finite closed interval. Okay, let's go. Okay, so next is the mean value theorem for integrals. Okay, that's THM is my abbreviation for theorem. So this is the mean value theorem for integrals. If f is continuous on a finite closed interval a comma b, then there exists a number c in a comma b such that f of c is equal to f, which is the average value of f, which again is 1 over b minus a times definite integral from a to b of f of x dx. Okay, so if f is continuous on a finite closed interval, then there exists a number c in that interval such that f, the value of f of that c, is the average value of that interval. Okay. So you have this. And what you mean by that, that is the definite from a to b of f of x dx is equal to f of c times b minus a. So I'm just multiplying, if you have this is equal to this, if you multiply both sides by b minus a, you get f of c times b minus a is equal to that differential. So you get this equation. So this is the mean value theorem for integrals above that line. Okay? Okay, so I'll give you a moment to look at it. Okay, so here's the next example. Since f of x is equal to 1 plus x squared is continuous on the interval -1, 2, the mean value theorem for integrals says there is some c in that interval, -1, 2, such that s dot t dot is the abbreviation for such that the definite rule from -1 to 2 of 1 plus x squared dx is equal to f of c times b minus a, which is 2 minus -1. This equation here. We have this equation for this situation. So here's the interval from -1 to 2, and you say that differential is equal to f of c times b, which is 2, minus a, which is -1. So using this equation right here that I circled for this situation, because f is continuous, this function f is continuous, right? Then there exists some c in that interval such that the definite integral is equal to f of c times the difference of this minus that, 2 minus -1. Which is the same as saying that this is equal to f of c times 2 minus -1, which is 3. Well, we calculated this definite integral already, and we got that this was 2. No, we got that this was so we got this was 6, because before we got that the f average was 2, right? We got what was 2 is we had 1 over, well, so we had the f average was 2 in that last example, right? So earlier we had that f average was equal to 1 over 2 minus -1 times the definite integral from -1 to 2 of 1 plus x squared dx. And what we got was that was equal to 2. That was the last board. Okay. So the f's of c here is the f average here. This is the f of c. And so that implies that f of c is equal to 1 over 2 minus -1 of that definite integral. Or just right from the same theorem. Here we got the f average, this is f, and this is equal to 2. And so what we have is that f of c is equal to 2. Well, f of x is 1 plus x squared. So we have that f of c is 2, so that means 1 plus c squared is 2. That's f of c, and it equals 2. And so that means c squared is 1. That implies c is plus or minus 1. 1 plus c squared is 2, c squared is 1, c is plus or minus 1. And so we do have some c in that interval such that this equation holds. Specifically, c is plus or minus 1. We actually have 2 values, but we know by the mean value theorem there's at least 1. The conclusion is there exists a number c in that interval such that that equation holds. There exists means that there's at least 1. And actually in this case there's 2, which is at least 1. Okay, so that's an example of using the mean value theorem. Okay, so that's the end of 4.4. So 4.5, the substitution rule. Okay, 4.5, the substitution rule. So here, let's look at this indefinite integral. Okay, so when we're using the fundamental theorem of calculus, right? The fundamental theorem of calculus. So the fundamental theorem of calculus says that the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f, right? And so the fundamental theorem of calculus makes it important to find an antiderivative of a function, okay? Or to find an indefinite integral of a function. In this case, it would be the function 2x times the square root of 1 plus x squared, right? So if I put limits here, and I turn this into finding a definite integral, then the fundamental theorem of calculus could be used as long as I can find an antiderivative. So finding an antiderivative of a function is extremely important in calculus. It allows us to calculate definite integrals, right? Okay, so finding an antiderivative of a function enables us to use the fundamental theorem of calculus to calculate it, okay? The problem is, though, is that some functions, it's difficult to find an antiderivative of it. It's not so simple. If we were to find an antiderivative of x squared, right, we could just say it's x cubed over 3 and then plus any constant c, right? If we want an antiderivative of cosine x, so the integral of cosine x dx is equal to sine x plus c. These are two examples where you can get the answer very quickly if you know enough math, right? You need to know that an antiderivative of cosine x is sine x. If you don't know that, then it's extremely difficult, right? If you know that already, it's very fast and it's very easy. In this case, though, you look at it and there's no simple formula yet for how to find an antiderivative. And so in order to have an easy way to do this, we need what's called the substitution rule. So in 4.5, we're going to learn the substitution rule, and that's a method of finding antiderivatives of stuff like this, okay? So we already have a method for finding integrals like this and this. We now need the substitution rule to find integrals like that. Okay, let's do that. Okay, so we're going to use the substitution rule. Let u equal 1 plus x squared. Du, the differential of u, is equal to 2x dx. Okay, so without explaining why, which is extremely complicated, without explaining why, I claim we can do the following. We can do this. Okay, so what I want you to do is just believe me. Okay, so if you take the integral of 2x times the square root of 1 plus x squared dx. First, this doesn't require much belief. I'm going to move the terms around. Square root of 1 plus x squared times 2x dx. Okay, so I just move it around. That's not where the belief part comes in. This is where I want you to believe. Now I'm going to substitute 1 plus x squared for u. It's going to be the square root of u. And then instead of 2x dx, I'm going to substitute du. And so what my claim is that I can do this. Okay, the equal sign I start here, what I want you to believe in is this, that this integral with the term with respect to x is equal to that integral with respect to u from these two equations. These are equations, this is an equation relating u with x and then relating the differential of u with the differential of x. Using those two equations, I want you to believe me that this integral is equal to that one. Okay? Well, what's that integral? That's equal to, using exponential form, that's integral of u to the 1/2 du. And so you just add 1 to the exponent, u to the 3/2 divided by the new exponent, u 3/2 over 3/2 plus c. That's equal to 2/3 u to the 3/2 plus c. And then, what was u originally? U is 1 plus x squared. So that's equal to 2/3 times 1 plus x squared raised to the 3/2 plus c. Okay. Okay, so that's 2/3 1 plus x squared to 3/2 plus c. That's the integral of 2x and the square root of 1 plus x squared dx. Okay, so believe that in that equal sign, believe me, and then you get that answer. Okay, and so that's using what's called the substitution rule. So this is an example of it. and I'm going to next write what the substitution rule is. But usually when you're learning calculus and you read the substitution rule, it doesn't make much sense. Even though this may not make much sense either, this is easier to understand than the rule itself. So the easiest way to learn the substitution rule is to figure out how to use it, and maybe down the road you fully understand what you're really doing and what it means. And so the easiest way to learn it is really doing something like this, just using it. And so that's why I'm going to bring this up first. Here's what you're seeing first is how to use it. That's probably what you'll be able to do at the end of the course. But if you can understand the rule, that is better than just being able to use it. Okay, so now I'm going to write down the substitution. Okay, so the substitution rule. So if u equals g of x is a differentiable function, so if u equals g of x is a differentiable function whose range is an interval capital I, and f is continuous on I, then the integral of f of g of x times g prime of x dx is equal to the integral of f of u du. Okay, and so as a note, you can think of dx and du as differentials. Okay? So you can think of those things as the two things I squiggly underlined as differentials. Okay. So the substitution rule, we're going to draw a line here. Above that line, the substitution rule. If u equals g of x is a differentiable function whose range is an interval I, and f is continuous on I, then the integral of f of g of x times g prime of x dx is equal to the integral of f of u du. And actually, that is what I used in the last example. Okay? So in the last example, when I said that the integral of the square root of 1 plus x squared times 2x dx is equal to the integral of the square root of u du, that is right in line with what the substitution rule is saying. Here, the g of x was the 1 plus x squared. F of t, the f function, was the square root of t. And so f of g of x would be the square root of 1 plus x squared. G prime of x is equal to 2x, and you have dx. So here, this integral is this is f, this is the integral of f of g of x, 2x is g prime of x, and with a dx at the end, and that's equal to the square root f of u. So here's f of u is the square root of u, and with a du at the end. See? So this matches up exactly with what the substitution rule says. G of x is a differentiable function. This is a differentiable function whose range is an interval I, and f is continuous on I. The range of g is the integral of all real numbers growing equal to 1. Those are all the set of all values of g. And f, which is the square root of t, is continuous on the interval from 1 to infinity. And so this is a little weird. It meets all the conditions of the substitution rule, and the conclusion of it is what I use to say that this integral is that one. And so when I start that one equation, one equation, I was using this, the conclusion of this theorem, and all the conditions were met by the problem, okay? But usually you won't, if you can use the substitution rule correctly, then that will be enough for the course. You will not have to know how to show all the conditions of the substitution rule hold up, okay? What I want you to be able to do is use the substitution rule correctly to find the correct value of a definite integral, okay? If you use it incorrectly, it's wrong. What you need to be able to do is use it correctly. Okay, so that's the substitution. Okay, so let's keep going. Okay, you can go back in the video to look at that again. It's also in the book. So it doesn't have to be the last time you see it. Okay. Example. Find the integral of x cubed cosine of x to the fourth plus 2 dx. Okay? We're going to use the substitution rule. And so what I'm going to do is I'm going to write the solution the way I want you to write the solution on an exam. Okay? So I will not be showing or justifying, I'm not going to be justifying why all the conditions of the substitution rule are met. Okay? Because I won't ask you to do that on an exam. So what I'll do is show you the things I expect from in an exam. Okay? So I'll let u equal x to the fourth plus 2. Then du is equal to 3x is equal to 4x cubed dx. Using the substitution rule, we get that the integral of x cubed cosine of x to the fourth plus 2 dx is equal to the integral of cosine of, well, u is what's inside, so cosine of u, and then, let me do this. I'm going to move the cosine here, cosine of x to the fourth plus 2. Now, there's an x cubed here, but the du has a 4x cubed. So I'm going to include a 4 here and have 4x cubed dx. But now I've multiplied this by 4, which will change its value. And so what I'm going to do is now I'm going to do the opposite of multiplying by 4. I'm going to multiply by 1/4 also. If you multiply something by both 4 and 1/4, you're multiplying it by 1 and you're not changing its value. Okay? So this equal sign holds. Because all I'm doing is moving the terms around in the integrand, and I'm multiplying by 4 and by 1/4. Okay? So those two things are equal. This is equal to, now looking at the way I've written this is 1/4 the integral of cosine of that. Well, what's x to the fourth plus 2? That's u. This is cosine of u. And then what's 4x cubed dx? That's du. So that's equal to 1/4 the integral of cosine of u du. And what's the integral of cosine of u du? It's sine of u plus c. So that's 1/4 sine of u plus c. Technically, it's 1/4 times, in brackets, sine of u plus c. But then if you multiply the constant you're adding by 1/4, you get another constant. And so it would be a waste of time to multiply the constant you get by 1/4 and then add it by a different constant. You can just write 1/4 sine of c, sine of u plus c. And that's equal to, well, u is x to the fourth plus 2, is equal to 1/4 sine of x to the fourth plus 2 plus c. Okay, so that integrand, the most general antiderivative of that function x cubed cosine of x to the fourth plus 2 is 1/4 sine of x to the fourth plus 2 plus c. So we found the integral there. We found the family of functions that are the antiderivatives are of x cubed cosine of x to the fourth plus 2 using the substitution rule. Okay, and so if you write your answer like this, then at the end of the semester, if you can write an answer to a problem like this, then I'll be very happy. Okay? You let u be something, find du, Then using the substitution rule, you start with the beginning here and you find it equal to what? Okay, now why did I choose u equal x to the fourth plus 2? This is the creative, one of the two most creative parts of the solution, right? You're not given a u in the beginning. You have to find a u that will help you get the answer. And so the hint for me to finding u in this problem is the fact that you have cosine of x to the fourth plus 2. And so what that tells me is that x to the fourth plus 2 is like the problem, right? X to the fourth plus 2 is finding this integral difficult because it's not cosine of x, which would be sine x as an antiderivative. It would be cosine of x to the fourth plus 2. And that's hard to find, right? So x to the fourth plus 2 is like the problem. It's the most difficult part of that integrand. So why not try letting u be that, okay? And so one hint to finding the correct u to use the substitution rule is sometimes you want to let u be the most difficult part of your expression. And oftentimes, a lot of the times, especially in difficult examples, a lot of times the u you have to choose is just the most difficult part of the expression. Okay? And then maybe it's not difficult and it's easy. Okay, so let u be that, the u you find is that, and then you rewrite your expression in a way that you could just easily substitute u and du into the integrand to replace all the x's with u's. Okay, so the other hurdle is this, the fact that du is equal to 4/3 x cubed. In the original problem, we only have x cubed dx in the integrand, after the integral sign. And so what we're missing is a 4. And so the second creative part of this solution is the fact that we're missing something, right? We're missing the 4 here. And so the solution, if you're missing something, is to put the thing in there that you're missing, right? So if we're missing a 4, then put a 4 there so you're not missing it anymore, okay? So we need a 4 here so that we get 4x cubed dx so we can replace it with du. So the solution to missing a 4 is to put the number 4 there. And then, if you put the number 4 in there deliberately because you're missing it, then you might think the next question, well, what do I do after I put a 4 there? If that means I'm multiplying it by 4, then that means to fix that, I have to also multiply it by 1/4. Okay? And so there's two easy solutions to finding the two difficult parts of this problem. One, what should u be? Let u be x to the fourth plus 2 because you're taking cosine of x to the fourth plus 2, and that's weird. So let u be x to the fourth plus 2. And that works, and so you move past that. So without even knowing the solution, you could just say, well, that's weird, let me let u be that. And that would work. Then, here, you need a 4x cubed dx, and you just say to yourself, what am I missing? A 4. Let me put it there, and then let me fix the problem I caused by putting it there by multiplying by 1/4. And there you go. The rest of it is actually pretty easy once you've had practice doing it. So once you've had practice doing integrals using u substitution, the problem will be deciding what u will be and the substitution part. And so in this problem, it can be difficult, but also be very easy if you just use those two tricks. Let u be the most difficult part of the expression, and then think, what am I missing? Put it there, and then fix the problem by multiplying by the reciprocal of that number. Okay? Okay, so that's another example of calculating an integral using u substitution. Let's do another example. We want to find the antiderivative of this integral of square root of 2x plus 1 dx. Find that. Okay? So let u equal. So now think before I write it down, what would you let u be? Right? So you're at home right now watching this video, or wherever you are watching this video. What should u be? It should be 2x plus 1. That's the weird part, right? You're taking the integral of the square root of 2x plus 1. So let u be 2x plus 1. So let u equal 2x plus 1. Right? Don't let u be the square root of 2x plus 1. You want u to be something hopefully simple. Right? You want u itself to be simple. Hopefully. Not always, but you'd prefer it if the u you chose was simple. If you let u be the square root of 2x plus 1, then that's complicated and it's not going to help. The u I chose here is simple. It's 2x plus 1. It's very simple. Okay, so u is 2x plus 1. Then du is 2 dx. Okay? By u substitution, by the substitution rule, it's also called u substitution. By the substitution rule, we get that the integral of the square root of 2x plus 1 dx is equal to the integral of the square root of, well, I was almost going to substitute here. So we have, that would be the square root of u, but dx needs a 2, right? And so then I ask myself the question, what am I missing? I'm missing a 2 here. So let me fix that. This is going to be the integral of the square root of 2x plus 1. Then I'm going to put what I'm missing here, a 2 here. So now I have a 2. And to fix that, multiply by 2, I'm going to multiply the outside by 1/2. So that equal holds. This equals this, because this is this expression multiplied by 2 and then by 1/2. Now I'm going to substitute u. This is 1/2 the integral of the square root of 2x plus 1, which is u, 2 dx, which is du. There, I can now just use u substitution. And now it's easy from here. This is equal to 1/2 the integral. Change this to u to 1/2 du. So now I'm expressing the square root of u instead of in root form in exponential form. Now what's the integral of that? That's 1/2 times u to the 3/2. 1/2 plus 1 is 3/2 divided by the new exponent, which is 3/2. And so that's plus c. Okay, again, this is technically something plus c, and then you're multiplying 1/2 times that c, and then you're getting another constant. I'm just going to skip that step and then plus c at the end. So this is equal to 1/2 times the reciprocal of 3/2, because 3/2 is in the denominator, so if I move it to numerator, I flip it and get times 2/3 u to the 3/2 plus c. And that's equal to 1/2 times 2/3 is 1/3. That's 1/3. U to the 3/2. U is 2x plus 1. So it's 2x plus 1 to the 3/2 plus c. And that is the answer. So the integral of square root of 2x plus 1 dx is 1/3 2x plus 1 to the 3/2 plus c. Okay. And so now this is another example using the substitution rule. Okay, let's do another one. Okay, so here's another one. Find the integral of x over the square root of 1 minus 4x squared dx. Okay, so we're going to find that integral. So first thing, question is, what do you let u be? So I'm going to let u equal, and now what's the weirdest part of that integrand? What is the weirdest part of x divided by the square root of 1 minus 4x squared? A simple u, a simple expression, that's the weirdest part. That would be 1 minus 4x squared in the square root. So let u equal 1 minus 4x squared. So I can do that without looking at anything else, right? What's the weirdest thing? It's in the square root there, 1 minus 4x squared. And so I'm blindly doing this, right? So I don't know whether that u will work or not. But one good way to guess at what u is, again, is just the weirdest part. So the weirdest thing is the 1 minus 4x squared, and it's a simple expression for u, right? You usually don't want u to be something complicated, unless you're doing a very difficult example. This is the beginning, and so this is the easy problem, okay? So u equals 1 minus 4x squared. We'll let u equal 1 minus 4x squared. Then du is equal to negative 8x dx. Okay, so then let u equal 1 minus 4x squared, then du is equal to negative 8x dx. Okay, by the substitution rule, we get the integral of x over square root of 1 minus 4x squared dx. Well, I'm going to substitute u here for 1 minus 4x squared. But before I do that, let's think about the fact if I substitute the square root there for what's in the square root there for u, how do I substitute the x for an expression of u? Well, if u is 1 minus 4x squared, I have the dx here. So du is negative 8x dx. And so, okay, so I'm going to substitute the 1 minus 4x squared for u here in the square root. And I still have an x dx. And so then I ask the question, what am I missing? I'm missing a negative 8 here. So this is, I'm going to write this another way. This is the integral of 1 over the square root 1 minus 4x squared times x dx. X dx, right? I'm missing a negative 8. So I'm going to fix that by putting a negative 8 there. I'm going to leave space here. This is the integral of 1 over the square root of 1 minus 4x squared. And then I'm going to put a negative 8 in front and get negative 8x dx. And if I put a negative 8 there, I have to multiply by negative 1/8. Negative 1/8. Because negative 8 times negative 1/8 is 1. And multiplying by 1 doesn't change the value of the integral. Now I can substitute this for du, and in there I can put a u. And so I can replace all the x's here with expressions of u. So this is equal to negative 1/8, the integral of 1 over the square root of u du, using the substitution rule. Okay? 1 over the square root of u times du, negative 1/8 of that. That's equal to negative 1/8 times the integral. This is u to the negative 1/2 du. So I'm just writing in exponential form 1 over the square root of u. It's u to the negative 1/2. Okay. Okay, and then so u negative 1/2, the integral of that, you add 1 to the exponent, and you get negative 1/2 plus 1 is 1/2. So it's u to the 1/2 divided by the new exponent 1/2. And then that plus c. And again, when you multiply the negative 1/8, you would get a plus c here, and you multiply the c by negative 1/8 and get another constant. I'm skipping that step. I'm going right to just adding a plus c at the end. Okay, and so this is equal to, so if I take negative 1/8 and divide it by 1/2, dividing by 1/2 is the same as multiplying by the reciprocal of 1/2, multiplying by 2 over 1 or 2. So negative 1/8 times 2 is negative 1/4. This is equal to negative 1/4 u to the 1/2. So u is 1 minus 4x squared. So that's 1 minus 4x squared to the 1/2 plus c. Okay, so it's equal to negative 1/4 times 1 minus 4x squared to the 1/2 plus c. Okay, so that integral is equal to that. Good. Okay, so that's another example using the substitution rule. Let's do another example. So the best way to learn mathematics is just to do lots of problems, proofs, and examples. Okay. So here's another example. Calculate the integral of cosine of 5x dx. Okay, so calculate that integral, indefinite integral. So we're going to let solution. Okay, so ask the question again, what's the weirdest part of that integral? It's the 5x. Okay, so we'll let u equal 5x. Then du is equal to 5 dx by the substitution rule. So I'm just pretty much writing almost the same thing every time. I'm just writing let u be something, then u equal that. By the substitution rule, we get that. So see how my response is almost exactly the same. I'm just choosing a u that determines my du, and by the substitution rule, we get that the integral, now I rewrite the integral that I'm going to find. In this case, it's the integral of cosine of 5x dx. See, I'm just following kind of a procedure here in every example. So it's pretty much the same thing, just a different u, okay? Now if I plug in a u here, I have a cosine of u, but what am I missing? I'm missing a 5 in front of the dx. So in order to substitute to u, I need a 5 dx, I don't have dx. So let me put what I'm missing there. So I'm going to leave space. This is the integral of cosine of 5x. And then I'm missing a 5, so let me get what I'm missing. Now that's a 5, I have it. That means I'm multiplying by 5. I fix that by multiplying the outside by the reciprocal, which is 1/5. Okay, this is almost the exact same thing. So this is equal to, now I'm going to use u substitution. This is 1/5 the integral of cosine of 5x. What's 5x? 5x is u, so that's cosine of u. 5 dx is du. So that's 1/5 cosine of u du. Okay, that's equal to 1/5 times the integral of cosine of u, which is sine u, and then plus c. I'm just going to do plus c here. Okay, skipping one minor algebra step, which ends up with the same result. 1/5 sine of u. Now I'm going to bring back my expression of x. So sine of u means sine of 5x, and then plus c. So the answer is 1/5 sine of 5x plus c. That's the integral of cosine of 5x dx. And we're done. That's another answer to another problem. Calculate the integral of cosine of 5x dx. Okay? Okay, good. So we're good with that. Okay, let's keep going. Well, it's also good as lining up your equal signs, right? If you write lots of equal signs, if you line them up like this, it's much easier to read your work. If you just line up the equal signs and it's one line after the other, and everything is lined up. See, the equal signs are lined up, the 1/5 are lined up, the integrals here are lined up, the trig functions are lined up. I put a 5 here, so that. But I'm trying to make things as orderly as possible, and I'm lining up things that are identical. The equal signs are right one below the other one, the 1/5 are right below each other, the integrals are below until they're gone, now there's no more integrals. And so if you present your work neatly like this, the reader can read your work much easier. Okay? All right. The substitution rule for definite integrals. Okay. If g prime is continuous, on finite closed interval a comma b, and f is continuous, and f is continuous on the range of u equals g of x, then the difference from a to b of f of g of x, g prime of x, dx, then equals the difference from g of a to g of b of f of u du. Okay? So this is the substitution rule for definite integrals, and it looks even more confusing than the substitution rule for indefinite integrals. Okay? It's only harder. Okay, so if g prime is continuous on the finite closed interval a comma b, and f is continuous on the range of u equals g of x, then the definite integral from a to b of f of g of x times g prime of x dx is equal to the definite integral from g of a to g of b of f of u du. Okay, that's the substitution rule for definite integrals, and so I know you don't understand what I just said. And so again, the easiest way to use this the easy way to understand this is to, or grasp it, is to use it in a problem. and understand how to use it, right? So the substitution rule hopefully before started making more sense when you saw me do 4 or 5 examples where I was doing almost the exact same thing, and it became kind of formulaic as to how you use it. And so you can do that with this kind of also, I guess. You just keep using it correctly in the same exact way, follow a set procedure for doing it and that's correct, and you can use it correctly without understanding any of that. Okay, so at this stage of your mathematical learning, this can be very difficult. Okay, so let's use it correctly in order to start understanding what that means. Okay, so let's do that. I'm gonna have to erase it though, because I need the space for the example. Okay. Okay, so normally in a mathematical proof, well, usually the idea in doing a correct mathematical proof means you use a theorem when you know the conditions of the theorem are satisfied. If you know all the conditions of the theorem are satisfied, you could then use the conclusion of that theorem, right? But here, and as in a lot of other examples, at your level, we will not always worry about making sure the conditions of a theorem are justified. So you need to be able to use theorems correctly in the right situations. But I will not require an exam for you to justify using the theorem. Okay, you kind of have to intuitively know when the right time to use the theorem is. All right, so let's do an example. Okay, so evaluate the definite integral from 1 to 2 dx over 3 minus 5x squared. Okay, let's find that definite integral using the theorem. Okay, solution. It's the substitution rule for definite integrals. Okay, so solution. Again, let's basically think of this substitution rule as we did originally. What is the weirdest part of that integrand? The integrand is 1 over 3 minus 5x squared. Now, we want to choose a u that would make that simpler, and we want the u we choose to be simple. We don't want u to be 3 minus 5x in parentheses squared. The squared would make that more difficult. That would make it more complicated. We want to make u as simple as possible. So let u equal 3 minus 5x. That's a simple u, right? 3 minus 5x is what's being squared in the denominator. Don't let u be 3 minus 5x in parentheses squared. That's more complicated. Maybe in other examples you need to, but we're starting from the beginning, and so right now, this will be fine. Okay, so let u equal 3 minus 5x. Then du is equal to negative 5 dx. By the substitution rule, for definite integrals, here it's for definite integral. So by substituting for definite integrals, we get, and I got that to fit in that line. Okay, so by substitution rule for definite integrals, we get the definite integral from 1 to 2 of dx over 3 minus 5x in parentheses squared is equal to, now I want to substitute everything for u. The 3 minus 5x will be replaced with u. But what am I missing here? I'm missing a negative 5 to put in front of the dx, to replace negative 5 dx with du. And so let me put in what I'm missing. So this is 1 over 3 minus 5x in parentheses squared. That'll be 1 over u squared. But now, instead of just dx here, I'm going to put a negative 5 in front. So I put in the negative 5 I'm missing to substitute for du here. But if I put in negative 5, I need to multiply by its reciprocal, which is negative 1/5. 1 over negative 5, which is negative 1/5. Right? Multiplying by negative 5 and multiplying by negative 1/5 cancel each other out, and so I'm multiplying by 1, and so I'm keeping the value of the definite integral the same. When you multiply a number, this is a number. When I multiply a number by 1, it's still the same number. Okay, now I'm going to substitute by u. This is negative 1/5. The integral, I'm going to come back to these limits later. 1 over 3 minus 5x squared is 1 over 3 minus 5x, which is u, squared. Negative 5 dx is du. And so here, 1 over 3 minus 5x squared times negative 5 dx becomes 1 over u squared du. 3 minus 5x is u, so that's u squared, 1 over u squared, times negative 5 dx, which is du. Make sense? Now I've substituted all of this in terms of x instead in terms of u. The one last thing, so far I've done the same thing I did for u substitution for an indefinite integral. What's now added in addition to that is I have limits of integration here using x values. These are lower and upper limits of this integral where the integral is with respect to x. Now it's respect to u. So what I need are two values here and here that correspond with the x values here. And so the value I put here is the value for u, because that's the variable I'm using here. It's the value of this variable, given that the value of x, that variable is 1. So if x is 1, u is 3 minus 5 times 1. That's u is 3 minus 5, which is negative 2. And so a negative 2 goes there. When x is 2, u is 3 minus 5 times 2, 3 minus 10, which is negative 7. So a negative 7 goes there. And so u substitution for definite integrals is almost the same as u substitution for indefinite integrals, except in addition to doing what you did before, you have to change the limits of integration with respect to one variable to new limits of integration with respect to another variable. To do that, you take these values of this variable, plug them into the equation relating the two variables, and correspondingly, you get the values of the other variable. So when x is 1, you get u is negative 2. When x is 2, you get u is negative 7. So this equation relating u and x tells you for these limits of integration using x, you get these limits of integration using u. Okay, that's the one additional thing you add on to the u substitution for indefinite integrals when doing u substitution for definite integrals. Okay, a definite integral has lower and upper limits here. An indefinite integral doesn't have limits of integration. Right? Okay, so now we're going to calculate that. So now it's just a simple calculation of a definite integral and multiplying by negative 1/5. So this is negative 1/5 times that. Now I'm going to use, so I'm actually just going to do, right now I'm just going to change this to exponential form. So this is the integral of u to negative 2 du. Same limits of integration. So this is negative 1/5 times, an antiderivative of u to negative 2 is u to negative 1 divided by negative 1. And so I'm going to take that and evaluate it from negative 2 to negative 7. Okay? Another, I guess, one more thing is you're calculating a definite integral now, so you're not going to have a plus c at the end. Right? Okay, so an antiderivative of this, of u to negative 2, u to negative 1, negative 1, and you evaluate from the lower limit, negative 2, to the upper limit, negative 7. So that's equal to negative 1/5 times negative 1, because dividing by negative 1 is the same as multiplying by negative 1. You get 1/5 u to negative 1 evaluated from negative 2 to negative 7. And that's equal to 1/5 times. Now u to negative 1 is negative 7 to negative 1 minus negative 2 to negative 1. Raising something to negative 1 is just 1 over that. This is 1/5 times 1 over negative 7 minus 1 over negative 2. So that negative 2 is for this step up here. For that, this is separate. So this is 1/5 times negative 1/7 minus negative 1/2. So that's negative 1/7 plus 1/2. So this is 1/5 times, well, so negative 1/7 plus 1/2. Let me think of 14ths. So that's negative 2/14 plus 7/14. That's 5/14. So it's 1/5 times 5/14. That's equal to 1/14. That's just calculating that. You get 1/14. That's the answer. Okay, so that definite integral using the substitution rule for definite integrals, you get that definite integral is equal to 1 over 14. Okay, and so that problem is also done. Okay, and so now that is that problem done also. Okay, so we're almost done with this section and this chapter. So next is integrals of symmetric functions. Okay, so integrals of symmetric functions. Suppose f is continuous. On the interval from negative a to a. Part A, if f is even, by f is even, you mean f of negative x equals negative equals f of x. F is even means f of negative x equals f of x for all x. So if f is even, then the integral from negative a to a of f of x dx is equal to, I'm going to have to move this down so you have more room to write this and write the same thing. Then the integral from negative a to a of f of x dx is equal to 2 times the differential from 0 to a of f of x dx. Okay, what's happening here is that, let's say you have in this case, cosine x is a symmetric function. So let's say we look at cosine x from negative pi over 2 to pi over 2. This is y equals cosine x from negative pi over 2 to pi over 2 on that integral. Then this is an even function. Because if you take f of x, that's equal to f of negative x. Right? It's symmetric about the y-axis. And so let's say f of 1 is the same as f of negative 1. Cosine of 1 is the same as cosine of negative 1. Cosine of 1 equals cosine of negative 1. Okay? And so if you were to integrate, so integrating cosine from negative pi over 2 to pi over 2, where this is an even function, instead of integrating from negative pi over 2 to pi over 2, you could integrate from 0 to pi over 2. Right? If you want to find this entire area, if instead of integrating from negative pi over 2 to pi over 2, if instead you just integrate from 0 to pi over 2, then what you know is, by the fact that it's an even function, is that integrating from 0 to pi over 2 is half the area of integrating from negative pi over 2 to pi over 2. And so when you get half of this area, by integrating only from 0 to pi over 2, you just have to multiply it by 2 to get the integral from negative pi over 2 to pi over 2. So this is one example of what part A is saying. If f is an even function, meaning it's symmetric about the y-axis, or f of negative x equals f of x for all x, in that integral, then the integral from negative a to a of f x dx is equal to 2 times the integral from 0 to a of f of x dx. That's part A. Now part B. Part B is if f is odd, which means that f of negative x equals negative f of x for all x in the integral. Then the integral from negative a to a of f of x dx is equal to 0. Then the integral is 0. Okay, so if you find calculating definite integrals difficult, hope for a problem where you have a function that's odd, and it looks like that because the answer is 0. You don't have to do anything. You're just going to write equals 0. If you're doing it in the right situation, it's right. You can't just say every integral is 0. But for that situation, it's equal to 0. Okay, so to illustrate what's happening in this problem, let's say you take the graph of sine x. Sine x is odd. So if you take the graph of sine x, let's say you take sine x from negative pi to pi. And let's say you want to find the definite integral from negative pi to pi of sine x dx. Well, sine x has the property that sine of negative x equals negative sine of x. That's the same as saying f of negative x equals negative f of x, where f of x is sine x. So if f of x is sine x, then f of negative x is sine of negative x, and negative f of x is negative sine x. But this equation holds for sine. It's true that sine of negative x equals negative sine of x. For instance, if you take pi over 2, sine of negative pi over 2, sine of negative pi over 2 is the negative of sine of pi over 2. Sine of pi over 2 is 1, and sine of negative pi over 2 is negative 1. So if x is, so here, if x is pi over 2, then this equation says sine of negative pi over 2, which is negative 1, is equal to the negative of sine of pi over 2, which is 1. Negative 1 equals negative 1. That holds for that x. The rules for any x. So if you take, so that's symmetry about the origin, it's called. So being odd means it's symmetric about the origin. Even is symmetry about the y-axis. So this is symmetry about the y-axis. And this is symmetry about the origin. Okay, so symmetry about the y-axis means, right, you can flip it about over the y-axis. And symmetry about the origin means if you draw a straight line through the origin in such a way that it crosses the graph at 2 points. If I take this value here, where the line crosses the graph here, the x value here, if I take the negative of that x value, then the value of the graph is the negative of what it is here. The height here, I take this x point, now take the negative x value, the height here, negate the height there, and you get that. This height is this height, this distance is that distance. That's symmetry about the origin. That's where a function is odd, when the function is symmetry about the origin. And then the integral from negative a to a of f x dx is 0, right? This has to be the negative of that, okay? If you're doing integral from negative 7 to 7 of an odd function, it's 0. If you do negative 9 to 7, it's not 0, not necessarily, okay? It may be, but probably not. You can't say it does equal 0. Okay. Okay, so those are integrals of symmetric functions, a and b, and this is the picture of the string b. Okay, so very quickly, we'll do one more example. So example. Find the integral from negative 2 to 2 of x to the 6th plus 1 dx. Solution. Okay, so the integral from negative 2 to 2 of x to the 6th plus 1 dx. Well, is x to the 6th plus 1 an even function or an odd function? Well, let's say f of x is equal to x to the 6th plus 1. F of negative x is equal to negative x to the 6th plus 1. And if negative x to the 6th is the same as x to the 6th plus 1, which is f of x. So f of negative x equals f of x for any x. That means f is even. That implies f is even. And so by symmetry integrals of symmetric functions, we know that this integral from negative 2 to 2 is 2 times the integral from 0 to 2 of x to the 6 plus 1 dx, because the function x to the 6 plus 1 is even. And so you can calculate this integral from 0 to 2 instead of from negative 2 to 2 and just multiply it by 2. Okay, so that's our justification for that equal sign. Okay? The fact that f is even allows us to do that. Okay, and so now we're going to quickly calculate this integral. So an antiderivative of x to the 6 plus 1 is x to the 7th over 7 plus x. We're evaluating from 0 to 2. So 2 times x to the 7th over 7 plus x evaluated from 0 to 2. That's by the theorem of calculus. Okay, this is equal to 2 times, plugging 2 in here, is 2 to the 7th over 7 plus 2, minus plugging 0, 0 to the 7th over 7 plus 0. Okay, and that's equal to 2 times 2 to the 7th, that's 128 over 7 plus 2, and then minus 0, so it's just that times that. Okay, plus 2 here is 14 sevenths, so this is equal to 2 times 128 plus 14, which is 142 over 7. Okay, is 14, 38, 42. Then multiply it by 2, you get 284 over 7. And in simplest form, that's 40.56. Okay? But that's not rounded to the nearest hundredth. That's 40.57. That's rounded to the nearest hundredth. Okay? So 284 over 7 is 40.57 rounded to the nearest hundredth. In my head. Okay. Yeah, okay, that's good. Okay. Okay, so that's the answer to that example. Okay, and so we are now done with this section. Actually, let me just do one more example. So cover this completely. Examples. Example, let f of x equal to tan x over 1 plus x squared plus x to the 4th. Okay, so we need an odd function. So let's look at this. So we're going to find the integral from -1 to 1 of f of x dx. Okay, so if you could show f is an odd function, then this is going to be 0. Okay, but you have to show it's an odd function. So solution. Well, you have to know that's an odd function. Well, f of -x. So let's define what f is. So if you're going to show it's even or odd, find f of -x and see what you get. This is tan of -x divided by 1 plus -x squared plus -x to the 4th. That's equal to tan of -x. I'm just going to do this one step at a time. Tan of -x over, well, -x squared and -x to the 4th is x squared and x to the 4th. So that's 1 plus x squared plus x to the 4th. Right? Okay, well, what's tan of -x? Tan of -x is actually an odd function of its own. If you look at the graph of tan of x, it looks like this. Okay, so you've seen the graph of tan x before in pre-calculus. Okay, that's the graph of tan x. It's an odd function. It has symmetry about the origin. If you take any point on the graph of tan, you'll find it's an odd function. Okay? This length is the same as that length, this height, and that height, the negative that. Tan is an odd function, so that means that tan of -x equals negative tan of x over 1 plus x squared plus x to the 4th. And so what did I just show? Well, tan of x over 1 plus x squared over plus x to the 4th, that's f of x. This is negative f of x. So f of -x equals negative f of x. And that implies that f is odd. F is an odd function. Okay, so since f is an odd, very odd function, the integral from -1 to 1 of f of x dx, when we're integrating from -1 to 1 with an odd function, we know from earlier that that's equal to 0. So the answer is that definite integral equals 0. Because I proved that f is an odd function, which means that the integral from -1 to 1 of that particular odd function is 0. All right, and so that concludes 4.5 and chapter 5. Okay, so I'll see you next time.